Now, over the past few weeks, we have studied Rn quite a bit. Rn, remember, is the set of all n-dimensional vectors, right? And there's all kinds of great properties that have proven useful. It has the commutative property of addition. If I take two vectors u and v, I add them together, it's the same as v plus u, right? The order of the summation doesn't matter. I have the associative property of addition. There exists an additive identity, specifically the zero vector. If I take any vector and add it to the zero vector, I get that vector that I started with back, unchanged. Okay? And I have an additive inverse. If I take any vector, there exists another vector, negative u, so that when I add them together, I get the zero vector. I have the distributive property of over vector addition and over scalar addition. I have the associative property of scalar multiplication. And I have the property of multiplication by 1. If I multiply a vector by scalar 1, it just gives me the original vector again. Okay, so I have all these lovely properties. Now I'm going to add two more that turns out to be really important and together kind of form a complete set. Rn is closed under vector addition. And Rn is closed under scalar multiplication. So we just talked about these two properties. To be closed under vector addition means if I take any two n-dimensional vectors and I add them together, the result will still be an n-dimensional vector with real numbers. It will still be in this set, right? It's almost so obvious that that we don't even think about it. Similarly, Rn is closed under scalar multiplication. If I have an n-dimensional vector and I multiply it by a scalar, any real numbered scalar, then the result will still be an n-dimensional vector with real numbers. It will still be in this set. And so it's closed under scalar multiplication. Okay? We say a set that has all of these properties is a vector space. And so if it has all these properties, most of the nice results that we've looked at over the past several weeks, as long as the set has these properties, those results for the most part hold. Okay? In particular, of course, we're saying that Rn has all these properties. So Rn is a vector space. But as we'll see, Rn isn't the only kind of vector space. There are other sets, other spaces that possess all of these properties. And so they could also be termed a vector space. Okay, we're going to explore that in this section. I do want to just emphasize these two properties real quick. Being closed under vector addition, being closed under scalar multiplication, and why we really like these properties, why they're important to being a vector space. We got all these other properties here, and they're super nice too. But this one is kind of the one that gives us the real power here, these two here. Because if we put these together, these two properties imply that any linear combination of vectors in Rn is still a vector in Rn. And that's really what we want. Put these two together so that we could talk about linear combinations. Okay? And just to kind of prove it to you, that V1, V2, all the way to Vk be vectors in Rn. And A1, A2, all the way to AK be scalars. Okay, and let's take the linear combination here. A1, V1 plus A2, V2 all the way to AK, VK. Actually, make it a little bit easier to describe what's going on. Let me add an A3, V3 in there too. Okay. So first off, we know Rn is closed under scalar multiplication. So if I have a scalar and I multiply it by a vector, that means the product would still be a vector in Rn. Okay. So each one of these is just a scalar times a vector. So each one of these would still be a vector in Rn, an n-dimensional vector. Okay? So that's what we get from being closed under scalar multiplication. Being closed under vector addition, that means if I take any two vectors that are already in the set, they stay in the set. So if I take this vector and this vector in Rn and I add them together, the result will still be in Rn. And then if I take that result and add in this vector, the result will still be in Rn. And I can keep doing that until I add in the last vector, the result will still be in Rn. So this linear combination of vectors will still be in the same vector space. And that's one of the key properties of a vector space. It's closed under, because it's closed under vector addition and under scalar multiplication, that means it's closed for all linear combinations. Any linear combination of the vectors would still be in the set.